the frequencies at which VC and VL is maximum. Where VC is the voltage across the capacitor, VL is the voltage across the inductor. In series resonance, VC and VL are not maximum at resonant frequency. We know that VC equals to IXC, I is V by Z, and XC is 1 by omega C. V divided by Z is square root of R square plus omega L minus 1 by omega C whole square multiplied by 1 by omega C. Now squaring on both sides, we'll be getting VC square equals to V square divided by omega square C square of R square plus LCM omega C, that is omega square LC minus 1 whole square, which equals to V square divided by omega square R square C square plus omega square LC minus 1 whole square. The frequency at which VC is maximum can be obtained by differentiating VC and equating the first derivative to 0. Differentiating this equation, the dy d omega d by d omega, will be getting minus v square 2 omega naught c square r square plus 2 omega naught square lc minus 1 2 omega naught lc divided by omega naught square c square r square plus omega naught square lc minus 1 whole square equal to the power of 2. And we need to equate this to 0, then this term will be equal to 0. 2 omega naught c square r square plus 2 of omega naught square lc minus 1 2 omega naught lc equals to 0. To solve this, we'll be getting 2 omega naught square l square c plus cr square minus 2l equals to 0, or omega naught square equals to 1 by lc minus r square by 2l square, from which omega naught equals to square root of 1 by lc minus r square by 2l square. Then the frequency f naught is given by 1 by 2 pi square root of 1 by lc minus r square by 2l square. This is the frequency at which the voltage across the capacitor is maximum. Now let us find the frequency at which VL is maximum. So we know VL equals to I XL, that equals to V by Z. XL is nothing but omega L, that equals V omega L divided by square root of R square plus omega L minus 1 by omega C whole square. Now squaring on both sides, that is the whole square and whole square. Now VL square equals to V square omega square L square divided by R square plus omega L minus omega C whole square. Now for simplification, we will be getting V square omega to the power of 4 L square C square divided by omega square C square R square plus omega square LC minus 1 whole square. Now differentiating V with respect to omega and equating that with a 0, we will be getting the maximum, the frequency at which the VL is max. So differentiating this with respect to omega. Similarly, differentiating this with respect to omega and equating that to the 0. Now if you differentiate this, 2 omega square LC minus omega square C square R square minus 2 equals to 0. Omega square 2 LC minus C square R square equals to 2, from which omega square equals to 2 by 2 LC minus C square R square, from which omega equals to 1 by square root of LC minus C square R square by 2. The frequency f naught at which the VL is maximum is given by 1 by 2 pi multiplied by 1 by square root of LC minus C square R square by 2. From these two expressions, we can say that the maximum value of voltage across the capacitor occurs below the resonance frequency f naught. The maximum value of VL occurs above the resonant frequency f naught. If we consider FC frequency at which VC is max and FL is the frequency at which VL is max, FC is less than f naught, that is resonant frequency, and FL is more than f naught, that is resonant frequency. If R is as small, then Fc, Fl and F0 will be having the same value, that is 1 by 2 pi square root of 1 by Lc, or 1 by 2 pi root Lc. Effect of resistance and frequency response curve in series resonating circuits. The variation of current with frequency for two series RLC circuits having the same L and C but different values of R. These curves are referred as frequency response curves. The curve with the small resistance rises steeply and have a tall narrow peak, while the curve with the large resistance rises less steeply and have the low broad peak. Thus, the effect of large resistance is to flatten the curve. A circuit with flat frequency response will have large R, and this is more responsive, less selective at frequencies in the neighborhood of resonant frequency. On the other hand, the circuit for which the curve has tall narrow peak, that is small r, will be less responsive and more selective at the frequencies in the neighborhood of a resonant frequency.